Right, this is the first in a series of videos about electric fields, which follows on from the generic fields videos that I've already made about electric and gravitational fields. So we're going to have a quick look at just some basic ideas, just to recap from GCSE, then go on to Coulomb's law, which is a lot like Newton's law of gravitation, but for charges, then look at electric potential and electric field strength, where there are a lot of parallels with gravitational fields as well. So, really basic thing just to begin with. Bit of recap. Obviously, atoms, what are they made of? Well, made of a nucleus and electrons going around the nucleus. The nucleus is positive and the electrons are negative. In conductors, things that conduct electricity, one or more of the electrons are free to move around within the material. So things like metals and graphite have electrons that are free to move around. Insulators, on the other hand, don't have many free electrons to move around, so they're not that good at conducting electricity. And materials made of atoms, which is everything, pretty much, can be charged. They can gain a net electric charge, and the way you've probably done that is by rubbing two things together. So if I quickly duplicate this atom here, and maybe just make it a different color. If you rub two different substances together, like, I don't know, a plastic ruler on a jumper, or a balloon on your skin or your hair, sometimes, let's just split this diagram up a bit. Sometimes electrons can get transferred from one thing to the other, from one material to the other, if they're two different materials. So things can end up with a net charge by the transfer of electrons. So this thing here would end up with a net charge of being positive because it's just lost an electron. This bit here, this material here, would end up with a net charge negative because it's gained an electron. So that's a process you're probably familiar with. If you want to experiment with it, there's all sorts of ways you can test whether or not something you've rubbed has gained a charge. If you rub a ruler on your jumper and it's picked up a charge, you can bring it near a stream of water, a thin stream of water coming from a tap, and see if it deflects the stream of water without touching it. And it's quite an interesting explanation as to why that happens. You could also cut up a load of bits of paper, really small, and put them on the table, and then bring your ruler or whatever it is near to those tiny bits of paper, and if the ruler's got a charge, it will actually pick up those tiny bits of paper. Again, the explanation for that is quite interesting. You might want to think about it. So these are some basics. Finally, the attraction or repulsion of charges. So same as magnetism, in that like things repel, so two positive charges will repel each other, a positive and a negative charge will attract each other. So these two materials, once you've rubbed them together, they will actually attract. So if you were to somehow suspend them from a bit of thread, insulating thread, and bring them together, they would probably attract each other, because one would be positive and one would be negative. So, bit of recap there. What are the implications of this that you probably didn't consider at GCSE? Well, like charges repel, we've just said that. So if you charge an object by putting extra electrons on it or taking electrons away from it, that charge tries to spread itself out because the charges are repelling away from each other. And conductors allow charge to flow. So if you charge a conductor, then the charge will actually spread itself out over the whole surface of the conductor. If you charge part of an insulator, the charge gets stuck there because it can't flow. But a conductor, it can. So if you imagine over here, I've got a sphere which I've made conducting. Might be a ping pong ball which you can coat in graphite to make it conductive. If I were to plonk a load of electrons on this otherwise neutral sphere, perhaps from something I just rubbed or something like that with a cloth, what are all these electrons going to do? Well, since it's a conductor, the electrons repel each other, and they repel each other until they're all as far away from each other as they can be, which is by spreading themselves out all across the surface of the sphere. And obviously I've just drawn this as a circle, but you've got to imagine this is a 3D object. They're spread all over the surface because they repel each other and they are able to move. If we were then to bring another similar ping pong ball, which is also neutral, over and put it in contact with the original one, now there's even more surface for the electrons to spread themselves over, and because they're free to move, they're going to spread themselves all over the surface. They're as far away from each other as they can possibly be. Bit uneven this, but you get the idea. Okay, so charge spreads out on the surface of conductors. If you were then to separate these two conducting spheres, they would both now have a negative charge. It would have been shared out between them. So charge spreads out over the surface of conductors. Charge on the surface of insulators basically gets stuck wherever you put it. Now this little kid on the left here has gained a net electric charge by rubbing his or herself against this slide. How do we know the kid has a charge? Well, their hair is standing on end. Why is the hair standing on end? You've probably worked it out, but let's say the kid has gained a net positive charge by transferring electrons to the slide, for example. That positive charge is going to be spread all over the kid, and as you know, like charges repel, so the fact that the kid's head and the kid's hair, strands of hair, are all positive means that they're all going to repel each other. And now the strands of hair are extremely light and thin, so when they're all similarly charged, they actually repel each other so that they stand up and they increase the separation between each strand of hair. So that's what's happened. Now you notice at the top that the title for this page is earthing. So what's going to happen to this kid when they come off the slide and they come in contact with the earth? Well, the earth is essentially like a huge conducting sphere. You might not think that the earth is a brilliant conductor, but it's really reasonable. So you can just think of the earth like a huge conducting sphere, and therefore charge can spread itself out onto earth. Just like on the slide before where we had two spheres brought together, well, the same thing can happen with the earth. So if this kid, who I will try to get hold of now, come down here, if this kid comes in contact with the earth via some conducting path, like touching the earth with their hand or something like that, then this charge is going to spread itself out across the combined surface of the kid and the earth. But because the surface of the earth is so much bigger than the surface of the kid, some of these are all grouped together. Well, anyway, we'll get rid of those. They're going to be spread over somewhere down there. Because the surface of the earth is so much larger than the surface of the kid, essentially all the charge leaves the kid because it spreads itself over the surface of the earth. So the kid is essentially discharged because their charge has spread over the earth. So if you earth something which has a net charge, if you bring it in contact with the earth via some sort of conducting path, then the charge will spread out over the earth. Further to this, you can pull charge or push charge to or from the earth as well. We'll think about what that means in a second. Now, let's get these two spheres again. We've got a conducting sphere here with a negative charge. That charge has spread itself over the surface. We've got a neutral charged sphere here, and we're going to bring them close together but not let them touch. We didn't think about this before. Think about it in some more detail. Now, when we bring these two together, the electrons in the atoms of this sphere are free to move, and they're going to be repelled away from the negative charge on the surface of this sphere. So they're going to leave the atoms that they're hanging around and run away over here to this side of the sphere, leaving behind atoms with a net positive charge over here. So this sphere has become polarized, we say. The negative charge has been pushed to the right, leaving a positive charge on the left. Which is all well and good. Interesting things happen. You might want to think about what would happen to these two spheres if there was this sort of charge distribution. That question will be in the examples at the end. So this sphere here on the right has been polarized. If we take this one away, the electrons go back to where they came from, and we have a neutral sphere again. Well, that's very nice. Whoops. What if we bring the Earth into consideration? Okay. Now, if the sphere is isolated from the Earth via an insulating mat or something like that, exactly the same thing would happen as happened just then. The sphere would become polarized if I brought this object near it, and then it would become unpolarized when I took it away. But if we make a connection between this sphere and Earth, an electrical connection, a conducting connection, then something interesting happens. If you bring a negatively charged object near this conducting sphere, which is Earth, the electrons get repelled away, but they can get even further away. They don't just have to get stuck over here. They can actually transfer themselves onto the Earth and spread themselves around the Earth. Whoops, that was weird. Go back there, Earth. There we go. They can spread themselves over the Earth, leaving behind, wherever they left, this positive charge. Now, if we break the Earth connection and take this charged object away, we are left with a positively charged object here. So it's lost some of its charge to the Earth because that charge was pushed away when the negative object was brought near it. So you can charge objects by earthing them, bringing another charged object near them, and then breaking that Earth connection to either trap the electrons on the Earth or conversely on the charged object itself. So I think that's the end of that basic introduction, just on recapping some stuff from GCSE and building on it a bit. Have a go at the next video of examples to see if you can apply it.